Hello, my name is Wang Jintao. My topic is SSF, accelerating training of spiking neural networks with stabilized spiking floor. Spiking neural network, short for SN, is a new kind of neural network which simulates biological neurons' action potential process. Different from other artificial neural networks, neurons in SN uses binary spike chains as inputs and outputs. Typically, a neuron's behavior can be divided into four parts: getting input spikes, accumulating input as memory potential, generate a spike when memory potential exceeds threshold, reset memory potential after generating a spike. As we introduced before, SN generates a spike when memory potential exceeds threshold. This process is discrete, so classic BP method can't be directly used. To solve this problem, SG method uses a surrogate gradient replacing the original heaviest function during backpropagation, thus enabling the use of classic BP method. However, SG method's training cost is unstably high, especially with long time steps, as shown in this picture. When time steps grow longer, training time needed in SD method experience rapid growth. Among many reasons for this, SG's BPTT framework plays a very important character. Red shows the backpropagation process of a typical SG method, from which we can see it also has the backpropagation in the time domain. If we can find a way skipping it, training cost would greatly reduced. In some areas, like image classification, SN receives pixel values as input of each time step directly. This will lead to repeating spike chains, which we named as stabilized spiking floors. It's worth noting that stabilized spiking floors stands for repeating process of memory potential. Taking this neuron for example, its memory potential keeps on becoming 0.5, 1, 0.5, 1, and 1. What's more, study shows that if a spiking neuron gets several stabilized spiking floors as input, its output would also become a stabilized floor. So in these areas, all spike chains in SN can be viewed as stabilized spiking floors, while neurons are just transformers between input and output floors. Nevertheless, what happens inside them? By building relationship between floors directly, we can avoid the backpropagation in time domain. No matter how they look like, a neuron's input and output floor satisfy such a restrict. The whole input electricity equals to the whole output electricity is electricity left after the last time step. Considering that left electricity is much less than threshold, with long enough time steps, it can be dismissed. So we have the whole input electricity equals to the whole output electricity. Stabilized spiking flow Fi can be simply divided from input. However, a neuron's true output is a binary spike chain, so we need some assistance. We define R as average electricity lost in each spiking process. It will be calculated during inference and used as a constant in backpropagation. Then we can define stabilized output flow and build relationships between them. With these definitions, the backpropagation process would become like this. So stabilized spiking floor will successfully avoid the backpropagation in time domain, thus greatly reducing training cost. We applied our method on several representing frameworks and different datasets. All experience proven the effectiveness of our method. Specifically, our method achieves about 10 times speed up ratio when time steps equal to 80. In the meantime, our method has very influence on the performance. As shown below, all four candidate frameworks accelerated with SF, consistently achieving the classification accuracy on par with the original counterparts, proving the effectiveness of our method again. Thank you very much.